Welcome back. In this video, we'll be working on Example 1 from Appendix S of ASME B31.3. This example demonstrates typical model input and key design considerations as outlined in the code. In this part, we'll focus exclusively on the modeling process within Caesar 2. In the next video, we'll walk through the complete checking and analysis of this example. For your reference, I've uploaded the PDF of the drawing and model input details. You can find it in the Readbook of the Library section. Let's begin by creating a new file. Click on New and enter the file name as Tutorial 1. Next, select a folder location of your choice, where this model will be saved. Once done, click OK to proceed. After creating the file, Caesar 2 may take a few seconds to load the interface. You'll then see a pop-up window titled Review Current Units. This window allows you to verify the unit system being used for your project. For this tutorial, we'll be working with the English unit system, which is consistent with the requirements of ASME B31.3, Example 1. Click OK to confirm and continue. Now you will see a classic piping input. We are going to start modeling the system step by step. For your reference, I've attached the model input details and the drawing snapshot in the top right corner of the screen. We will use that data to create the model in Caesar 2. First, we'll begin by entering all the necessary input values, such as node numbers, coordinates, pipe size, material, and temperature pressure details. Let's proceed with filling in the input data. Now let's start with the pipe properties. We are using a 16-inch NPS diameter with Schedule 30 wall thickness, as specified in the drawing. Next, we enter the corrosion allowance as 0.063 inches and select the pipe material, ASTM A106 Grade B. Once the material is selected, Caesar 2 automatically fills in the material properties like modulus of elasticity, thermal expansion coefficient, and allowable stress. Now for the fluid properties. We enter the specific gravity as 1 sg. It will automatically calculate the values. Next, we define the design conditions. Temperature 1, 500 Fahrenheit. Temperature 2, 30 degrees Fahrenheit. Pressure 1, 500. Now we'll enter the insulation details. Set the insulation thickness to 5 inches. For the insulation density, the given value is 11.0 pounds per feet cubed, as shown in the reference table. In Caesar 2, we will enter this as 11 divided by 1,728, since the software expects the density in pounds per inch. Once entered, Caesar 2 will automatically convert and apply this value in the calculations. Also note that Caesar provides several common insulation density options in the drop-down menu, but in this case, we're using the manually calculated value for accuracy. And here's a helpful tip. If at any point you're unsure about a particular field or setting, just press F1 on your keyboard. Caesar 2 will open the relevant help documentation, giving you detailed guidance for that specific input window. Now that we've completed all the input properties, let's begin the modeling phase. First, we'll define the starting node numbers. We'll begin with node 10 as the starting point. The first spool, as per the drawing, runs 20 feet in the X direction. So we'll define the next node as 15, which will be placed 20 feet away from node 10 along the X-axis. In Caesar 2, we'll enter from node 10 to node 15, dx. 20 feet. This creates our first piping element, a straight horizontal run between node 10 and node 15. As we can see in the drawing, there is an anchor located at the starting node, node 10. To model this in Caesar 2, we'll apply a restraint at node 10. Click on the restraints. In the restraint definition window, set the node number to 10. Then from the drop-down menu, select Anch, which stands for anchor. This will apply a fully restrained anchor, fixing all 6 degrees of freedom, translational and rotational, at node 10. The anchor serves as a fixed boundary condition for the system and is critical for analyzing load distribution. Now click on the Continue option in Caesar 2. This feature automatically carries forward the previous pipe properties, such as diameter, material, and temperature, making it faster to build continuous piping runs without re-entering data. We'll now model the next spool, extending the piping layout as shown in the drawing. From node 15 to node 20, we have a 20-foot straight run in the plus X direction. In Caesar 2, we'll enter the following values. From node 15 to node 20, dx 20 feet. This creates the second straight pipe element, continuing in the X direction from the previous segment. Now, as we continue reviewing the drawing, we can see there's a support at node 20. This is a Y-axis hold-down support, which restricts vertical movement, but allows movement in other directions. To model this in Caesar 2, click on the restraints. In the Restraint Input window, enter node 20. Then, from the Direction drop-down menu, select Y. This applies a vertical restraint at node 20, preventing downward movement along the Y-axis. It simulates a typical pipe support, or rest, that holds the pipe vertically but allows thermal expansion horizontally. Continuing with the model, we can see in the drawing that there is another spool of 10 feet running straight from node 20. This segment continues in the plus X direction, ending at node 30. To model this in Caesar 2, set from node 20 to node 30, dx 10 feet. This creates the third piping element, maintaining the same direction and building up the pipeline geometry step by step. We now need to define a directional change using a bend. In Caesar 2, to do this, first, select element node 20 to 30, then double-click on the Bend option. After that, click on Continue option. Now we can model the vertical rise from node 30 to node 40. Enter dy 20 feet. This models the vertical spool accurately and includes the bend transition from the horizontal to the vertical direction, as shown in the layout drawing. Now for the final bend in this section of the model. Select the element from node 30 to node 40 and double-click to assign it as a bend. Next, we'll model the following horizontal spools. From node 40 to node 45, the pipe runs 10 feet in the plus X direction. So we'll enter from node 40 to node 45, dx 10 feet. Click Continue to carry forward the pipe properties. Then, from node 45 to node 50. The pipe continues another 20 feet in the plus X direction. Enter from node 45 to node 50, dx 20 feet. At node 50, we place an anchor as shown in the drawing. Click on the restraint icon, then select ANC from the drop-down menu to define a fixed anchor support. And with that, we've completed the first section of our Caesar 2 piping model, based on the layout provided in ASME B31.3 Example 1. In the next video, we'll move on to checking the model and performing the stress analysis. If you found this video helpful, Please consider sharing our app with your friends, and don't forget to rate and review us on the Play Store. Your support helps us keep creating valuable content for you.